So, effects of forces. So when a force acts on an object, it can change three things about an object. Can anyone give me one? Mitchell. Yep. Yep. Yeah. One more. James. What shape? There we go. Yep. So this, if you were here in second year, you've done this already. If you weren't, you probably come across this already. So if you, there's three sort of diagrams there. So if you apply a force to an object, say you've got a sponge ball and you squish it, you can change the shape of it. Direction, think of tennis racket. If you apply a force to a tennis ball, it'll go in the opposite direction. And speed, again, if you hit it just like that, it'll go quite slowly. If you really hit it, you can change the speed of a ball. Okay? So those three things, forces can change about an object. So we're going to look, this booklet, Newton's Laws, is a natural continuation from the kinematics booklet. And of course, when you have a test on this booklet, it will include the previous booklet, the kinematics booklet as well. So you need to keep on top of that. Okay, remember there's all those videos online to watch, and you can ask me questions. So mechanics is the branch of physics that deals with the motion of objects. Kinematics, which is the last booklet, the vectors and scalars, is the branch of mechanics concerned with the motion of objects without reference to forces that cause the motion. And dynamics, which is this booklet, is the branch of mechanics concerned with the motion of objects under the action of forces. Okay, so previously in the previous booklet you didn't really come across any forces. This booklet is all to do with forces and how they affect movement. Measuring forces, you're all aware of. To measure forces, you use spring balance or Newton meter or Newton balance. All words for the same thing. They are simply springs which have a marker attached beside a calibrated scale. So you've all seen these before. Okay, and the more you apply force, the marker moves down. Okay. The spring stretches in direct proportion to the force applied to it. Hooke's law. Those of you might remember that. The unit of measurement of force is of course newtons, and you need to be careful about the difference between forces. And remember, weight is also a force, so that is also in newtons. Okay, we'll talk about mass and weight later. So, pull of gravity. Next page. So in physics, it's important that we distinguish carefully between the terms mass and weight. Can anyone tell me the difference before reading on? Between mass and weight? Mitchell, you had your hand up? Yeah? Yeah? No, good. Yeah. You're on the right line. So mass is how much stuff is in something. Okay, so yeah, you're right. It's measured in kilograms, and so it's like how much is everything that we're made of, the bones and the blood and the everything. How that's the stuff that's in you. Okay, and that doesn't change no matter where you are. Okay, the weight is the force due to gravity. Yeah, so it's the force pulling you down towards the center of the Earth. Okay, and then obviously if you move to a different planet, then your weight could be different. Okay, so if you you have a small weight. Remember, your mass will stay the same. So the amount of kilograms, it will stay the same, or the amount of stones or pounds and ounces and things like that. But your weight in newtons could change depending on where you are. Even if you go up a really high mountain, your weight in newtons could be different, but your mass will stay the same because you haven't lost a leg or anything like that. Okay, so you still got the same amount of limbs, so your mass is the same, but your force due to gravity will be different because gravity is slightly different up a mountain, very different on different planets. Okay, is everyone happy with that? Because it's really important. Remember that. Okay. Right. So mass. So this page is really important. Mass of an object is a measure of the total amount of matter in the object. It's given the symbol m. The unit of measurement is the kilogram. And the mass of a particular object is the same everywhere. Your mass would be the same if it was measured on Earth or the Moon or another planet or in outer space. And 1 gram is, of course, 1,000th of a kilogram, so 0.001 kilograms. And mass can be measured using a top palm balance. So, when generally, because the English language is rubbish, we often use the terms incorrectly. So, when you say you go to Weight Watchers, you're actually Mass Watchers, but it doesn't quite have the same ring to it. Okay, so if you're measuring, yourself in kilograms or stones or anything like that, you're measuring your mass, you're not actually measuring your weight. If you're measuring yourself in newtons, I'm not sure anyone does that, then you'll be measuring your weight. So, the weight of an object is the force of gravity, or the gravitational force acting on the object, given the symbol W, and its unit of measurement is the Newton. The weight of a particular object depends on where it is measured. So, where on the planet or where on in the solar system it's measured. The weight of an object would be much smaller on the Moon than on Earth, because the Moon is much smaller than the Earth, so the gravitational pull is weak. In deep space, where the force of gravity is negligible, so where you can basically ignore it, the weight is also pretty much zero. Okay, but that only happens in really deep space. Weight can be measured by hanging an object from a Newton balance. Phil, you have a question? There's always asteroids coming towards the Earth. Asteroids hit the Earth all the time. I'm sure it will be fine. Okay, so, guys, this experiment you have probably done before, but we don't have enough equipment to do individually. But you've all seen these before. So basically, you get a Newton balance and you hang masses off it, and you measure the weight of that mass using a Newton balance. Okay. So a mass of 0.1 kilograms, so 100 grams, which would be the holder here, is attached to a Newton balance, as shown in the diagram. The weight of the mass is read on the Newton balance, and the attached mass is increased in steps of 0.1 kilograms. The weight of the total mass is noted each time. So I have got this here. So around that, so I'm not going to do each one because it's quite hard to watch, but this is all. So this is around about 1 Newton. Just go on 1 Newton. Okay. So if you add another one on, and you can't really see it very well. It's just below 3 Newtons. Yeah. So it will go 1, 2, 3, 4, 5. Well, it's slightly below, but we'll just write it down as 1, 2, 3, 4, 5 for the time being. So I'll tell you in a second. So the last column is weight divided by mass. So newtons divided by kilograms, newtons per kilogram. So 1 divided by 0.1 is 10. Yeah, you should be able to do that on your heads. 2 divided by 0.2. Yeah. 3 divided by 0.3. Yeah. Okay. Yeah. So when you were in second year, you would have used the gravitational field strength as 10 newtons per kilogram. Okay, so the ratio weight divided by mass is constant. It's constantly around about 10. Okay, but in National 5, you start to use it as 9.8 newtons per kilogram. Sorry? Yeah. Oh, the mass, yeah. So this is called the gravitational field strength. So where you have previously used 10, you'll now use 9.8. Okay. Some of the question booklets I think still use 10 because I think it was from like a older curriculum. So you'll just have to just watch the question. So the question says use 10 as gravitational field strength, use 10. Okay, but if it doesn't, use 9.8. So gravitational field strength is given the symbol lowercase g, and the unit of measurement of gravitational field strength is the Newton per kilogram. Okay, which you can write as N/kg, but as we get further up in our science, we start to write these things kg to the -1. It means the same thing. It's just a unit. You don't need to worry about putting in any indices or anything. It's just another way of writing this. So that -1 is instead of that sort of slash. So 9.8 on Earth is the gravitational field strength. Okay, but we already know that the gravity on other planets is different. Okay, I'm sure you've seen films before where you've seen that people floating around, things like that, and you've probably seen the moon landing. Gravity is different on different planets and different bodies. Okay, the moon's not a planet. So gravitational field strength at a point is defined as the gravitational force per unit mass at that point. So gravitational field strength is weight divided by mass. Or you might see it written down, weight, which is more common, is mass times by gravitational field strength. And remember, weight is in newtons, mass is in kilograms, and gravitational field strength is in newtons per kilogram. And near the surface of the Earth, gravitational field strength is 9.8 newtons per kilogram. So a mass of 1 kilogram experiences a force due to the pull of gravity of 9.8 newtons. And the gravitational field strength depends on the location of the universe. So at the bottom of that page, there is a table of various different bodies in the universe or in our solar system, and the gravitational field strength corresponding to them. kg, kilograms. So you can see there, they all have different gravitational field strengths. The moon is much smaller than Earth. Generally, the bigger the body, the bigger the gravitational field strength. Not always, but generally. Okay. And as you go away from the surface of the planet, the gravitational field strength decreases. That's what I said. If you go up a really high mountain, the gravitational field strength is slightly smaller because you're further away from the center of the planet. And in deep space, far from any planet or star, the gravitational field strength can be assumed to be zero. Because everything that has mass has a little bit of a gravitational field strength. So it means you just be still, because you wouldn't get pulled in either direction. You wouldn't, yeah. So even you, Finley, have your own gravitational field strength. But you're so small compared to everything that it doesn't really affect anything, and you don't attract anyone towards you. Yeah. Yeah, exactly. Right, guys. Okay, so calculating weights, W equals mg. Have a go at finding the mass. So a pupil has a mass of 50 kilograms on Earth. Show their mass and weight in different places using that table above. So have a go at filling that in. Hint, the mass is very easy. So remember, weight is 9.8. I mean, sorry, not weight. Gravitational field strength is 9.8 on Earth. Look at the equation. W equals, yeah. Chris, you shouldn't be turning around. You should be staying on your desk. Yeah, Maria, you got it. Yeah, 50-50. The mass is the same, yeah. Have you done this? Right, the answers you can check are up on the board. So the mass is the same, doesn't matter where you are, because remember the mass doesn't change. So you're going to do weight is mass times gravitational field strength. So for the moon, the gravitational field strength is 1.6, so 50 times 1.6. And for Jupiter, the gravitational field strength is 26.4, so it's going to be 50 times 26.4. Right, so what I'd like you guys to do, we're going to do a little bit of some revision questions on weight and mass. So I'd like you to read through actually the next page on friction. Unfortunately, we can't get the hovercraft out, but hopefully, once it's safer, we will do that. So read through page 6, then question booklets, pages 1 to 3, are all sort of on revision type things that you should already know. W equals mg kind of things, friction, forces. Okay?